We'll get there pretty quickly. Like I said, I'm going to speed through this, and I am recording it. I got the 8th lecture loaded up there, and every so often I'm finding that I can only really get one up at a time. When I try to batch 4 or 5 of them up, I think they crash into each other or do something. Okay, way back in page 144, and I think we're talking chapter 6, but it's equation 4.48 is this equation. And it's the sum of and to put it into into terms of this chapter, the sum of the chemical potentials of the various phases as the differential of what those phases are, the quantity in those phases. If you go down through there and you just keep in mind that we're talking constant temperature and pressure, and if you think of some of these phase changes, for example, ice melting to be water, it's really, typically we're looking at an isothermal and an isobaric situation. I mean, ice gets up to 0 degrees centigrade in the presence of water, and it just stays there until all the ice melts. So it's really, that phase transition from solid to liquid is happening isothermally. And then if we add that we're talking about an equilibrium, you get that delta G equals 0. And so you're going to get that I'm going to just derive this very quickly. The chemical potential of one phase, let's say the solid phase, is equal to the chemical potential of the other phase at equilibrium. At equilibrium, you have the condition there where the chemical potentials of the two phases are equal. The temperature of phase 1 equals the temperature of phase 2. The pressure, like I just said, I'm repeating myself, we're at constant temperature and pressure. So the temperatures are the same, the pressures are the same, the chemical potentials are the same in those. And what are some of these phase transitions? We have liquids going to gases, and we talk about a delta H of vaporization. What is the enthalpy change associated with a liquid going to a gas? We have solids going to liquids. So we have a solid, the delta H of fusion, and then we have solids going to gases, and we talk about the delta H of sublimation. And all of these in this direction, going from liquid to gas, is an endothermic process. It takes heat to get a liquid into a gas. It takes heat to get a solid melted into a liquid. And it takes heat to get a solid to sublimate into a gas. So dry ice is, with the introduction of heat, is sublimating into gaseous carbon dioxide. So in this direction, we're talking about an endothermic process, and going back in the opposite direction, we're talking about an exothermic process. So a gas like water vapor condensing and precipitating out as rain, turning a liquid, is actually an exothermic process. There's heat being released as the vapor condenses into the liquid form. I'll try not to bog down until we get to some equations and do some examples. Remember earlier we had this equation that Q equals M times the specific heat times the delta T. and when we're talking about the amount of heat to heat up aluminum or heat up water or whatever, we're getting to a little simpler thing. It's related. There's no delta T in this equation. I don't know if that's got an equation number in the book or not.
What's SH?
Specific heat. Now this was way back in, I don't know what, chapter 2, okay? When we just did the calorimetry equation. How do you calculate the amount of heat needed where M is the mass, specific heat of the substance, whether it be water or aluminum or iron or whatever, and then the temperature change. But you can see here for these phase changes at an isothermal condition, we don't have any delta T. So just the mass of the material times the delta H of that transition, whether it be that phase transition, whether it be vaporization or whatever, there's a simple equation to deal with it. Oh, just one other thing to think about. Let's see, the delta H, of fusion plus the delta H of vaporization equals the delta H of sublimation. And where does that come from? Well, just kind of think about it. The delta H of fusion, you have a solid going to a liquid, and vaporization, you have a liquid going to a gas, and sublimation, you have the solid going directly to the gas. Okay? So there is another little relationship there. Okay, phase transitions. We're familiar with this equation. Delta G equals delta H minus T delta S. In phase transitions, delta G is 0. So I'm cutting this right out of the book so you can see that I'm not writing them the way I usually write them, but the way the author usually writes them. The delta H of transition minus the temperature transition times the change in entropy of that transition equals 0. And this rearranges. This is the trivial equation right here. Okay?
How can that delta G be 0? Because like in the book, if you look at delta G of say water as a liquid versus water as a gas, it's two different values. So wouldn't there have to be a delta G between those transitions? Like of the transition?
Let's see. Okay, delta G of the water, delta G of the gas.
They're different values. So
they're delta G's of formations.
okay.
Those are delta G's of formations. So let's think about that. But what are you talking about? This or the previous equation?
Well, I'm just talking about because you said delta G's equals 0 for a phase transition, and since we have those delta G's in the book, and water is a liquid versus water is a gas for two different values, I was just thinking there had to be. Well, I was just wondering why there isn't a number here because that just didn't make sense to me.
Yeah, let's see. How would that wash away? So this is a delta G of this transition. The free energy of that transition, it's occurring at equilibrium. You know, this transition is occurring under equilibrium conditions. So the delta G of that transition is 0. Let's see. The delta H of formation of liquid water would be hydrogen plus oxygen gas forming hydrogen, H2O liquid. The delta G of formation of water as water vapor, you're saying?
Yeah.
Would be hydrogen plus oxygen forming H2O gas. So you get these two different delta G's. somehow I'm thinking I'd have to scratch it out to be sure, but somehow if we looked at the delta H, the enthalpy difference between that liquid water and that gaseous water, that's where you're probably going to see those differences in those delta G's of formations. Okay? I think you could sit down and scratch on that a little bit. Look at what is the enthalpy difference between, you're going to have a free energy difference between the liquid and the gas. You're going to have an enthalpy difference between the liquid and the gas. You're going to have an entropy difference between the liquid and the gas. And if all of that was taking place at 298 degrees Kelvin, you might find, it'd be a good homework problem, maybe, but you might find that those delta G's of formations of liquid water and gaseous water would reconcile to this. It should. Okay, I'm just saying right now it should. We'd have to grind it out to see if that's the case, because what we're going to have, we're going to have a delta H of vaporization going from that liquid water to that water vapor. There's going to be a delta H of vaporization, and there will be a delta S of that vaporization process, that transition. Okay, is that good enough for right now? I mean, we would have to back up and scratch through it.
Yeah.
But I see what intuitively you're saying. How does this make sense? And I think the math should make sense. Those delta G's of formations should not contradict this.
Yeah.
Okay? So it should all make sense. I'm not sure. I'm taking a stab at where it's going to reconcile, and it's going to reconcile around this delta H of vaporization or something like that. But they should reconcile, because mathematically, I mean, what you're seeing with PChem is it's pretty mathematically, well, it's certainly attempting to be mathematically precise in where it gets all these equations and where these fundamental thermodynamic properties come from. Okay, well, let's just take it from there. This will be the simplest equation for right now. You just hear basically what it's saying is if you know the delta H of the transition and the temperature at which that transition occurs, you can calculate a change in entropy, which let's just try to do that right now. And the quicker we grind through these, the quicker I can get to Chapter 5 homework. Calculate the change in entropy for the following phase transitions. And let's not worry about B. Let's just worry about A. We've got 1 mole of mercury. Let's get this equation back up here again. The delta S of this transition equals the delta H of this transition divided by T. 1 mole of mercury liquid freezes at its normal melting point. Here's T. The heat of fusion of mercury is 2.33 kilojoules per mole. All right, and just to kind of demonstrate how straightforward this is, so this delta H of fusion is going to be the delta S of fusion is the delta H of fusion divided by the temperature, the melting point, the melting point, which is the fusion temperature of fusion. So we have 2.33 kilojoules per mole. We have just 1 mole of material, and this is going to be got something?
I got a really small number.
Really?
Okay, I got 0.0099466382.
9946.
That's in kilojoules.
Yeah.
Yeah.
Is that right? Know what everybody's got?
Yep.
Okay. So I'm just trying to show you how to use your equation quickly. And then there's another one there for carbon tetrachloride. So here is a straightforward way of calculating a change in entropy. Let's see. What you do need to do is you got to stop for a moment and think about sine delta H of fusion. What are we doing here? Mercury liquid freezes. So to freeze it is going to what? Either take energy or release energy?
We're taking energy out, so it's going more ordered, so our entropy is going down.
Negative.
So it should be negative.
But the entropy is going to go down. The enthalpy is, we're going to actually be releasing. It's exothermic, right? We're going from liquid mercury to solid mercury, so that's exothermic. So this would actually be a negative. Negative?
Yep.
And our delta, and our delta S is coming out as negative. Just what we were saying. All right? So you should pause at the end of these calculations and ask, how did I set this up? Is it freezing? Is it melting? What's going on? Is that delta H going to be a positive or a negative number? Okay, the Clapeyron equation. Yeah, it shows that both of these forms basically are called the Clapeyron equation, and you can look at the derivation of them in the chapter, but the change in pressure over the change in temperature is equal to the change in the molar entropy divided by the change in molar volume. And
This would be the same as changing entropy over volume, because those molar values are going to cancel out.
yeah, basically.
Okay.
And all we've got here, this is infinitesimal changes in pressure and temperature. So that is the exact equation. But over a reasonable range of pressures and temperatures, this is a good approximation of that precise equation. And this is worth noting because when you do this calculation, you are not getting precisely the answer, but you're getting a good approximation of this relationship. So whatever it is you are seeking, whether it's what the pressure change was or what was the temperature change, knowing any other three of these, it's a good estimate. So let's just take that. Here's the equation. Say approximately. Estimate the pressure necessary to melt water at negative 10 degrees centigrade if the molar volume of liquid water is 18.01 milliliters and the molar volume of ice is 19.6 milliliters. Really pointing out there what we know, we understand that water actually expands as it freezes, which is a pretty unique property. Most everything contracts as it gets colder, and even as it crystallizes, it contracts. But ice has this quality about it. That's why all the lakes in town, the ice is on top of the lake. The fish like it that way, by the way. I mean, if ice was more was less dense. Here we're not looking at densities, we're looking at the volume. So it actually expands. It's got less density. If it was more dense than water, it would sink, and there'd be no broom hockey in the middle of winter. There would be, there would be this polar swimming contest to see who could swim in water that was minus 28 degrees centigrade, something like that. Okay. So delta S for this process. So we're given delta S. That's given. We're given the information to calculate the change in volume. Right? What else do we need? Oh, we're given the temperature. We're given the delta T. What's the delta T? Estimate the pressure necessary to melt water at minus 10 degrees centigrade. So what's delta T?
Probably go from 0 to 270 to maybe 0 to that negative 10 C, but you'd have to do it in Kelvin.
Okay, so the delta T is, we're comparing this to normal water. Normal water freezes at 0, and they're saying, okay, what pressure would be needed to, if you had a chunk of ice that was at minus 10 degrees centigrade, what pressure would be needed to actually cause it to melt, to convert back into the liquid phase at minus 10 degrees centigrade? Okay, so so delta T is given 0 versus minus 10, and delta P, normal pressure, is 1. So P1 is 1, P2 is unknown. So how many times bigger than the normal pressure of ice under normal temperature? So delta P is going to equal delta S divided by delta V times delta T. Delta V,
Maybe final minus initial, right?
yeah, so final is going to be the liquid water, right? Yeah, the liquid water. It's going to turn into a liquid finally, so it's going to be final milliliters minus the initially it is solid, it's ice, and it has that volume, and we're going to have to convert those milliliters to liters, right? And up here we're going to have a delta T of minus 10 and minus 10K, minus 10C is no difference. They're the same, the degree is the same size. And then the author is giving us that 1 liter bar per joule. So K is crossing out, milliliters are going to cross out. And if we put in here 1 liter bar per 100 joules, joules will cross out and we will get to what? Bars. And this is the Clapeyron equation. It's a Y. Are you getting something like, what are you getting something like?
Negative 355.
I got 338.6.
338.6 bars?
How are you getting a
But-
positive number?
What temperature did you guys use? Just minus 10?
263.
Oh, it's 2. Why is it 263?
It's a negative 10.
Well,
Delta T.
it's a delta T.
Oh, yeah.
It's delta T. Yeah.
So normal liquid water, normal ice is at 0, right?
Right. So the temperature change is 10 degrees.
10 degrees.
Negative 10.
Minus
Negative 10. Yep.
And then do positive 22.04 joules per Kelvin, and then negative 0.0065.
Let me punch these in because I see a different number here.
Maybe it is a math.
Dom, what'd you get?
I got 338.62 bars.
You got 1352.
That's what I got. Positive?
Yeah. That's a lot of bars.
Yeah, Dominic.
It's 10 to 30.
That's in bars. Bars, 10%.
So what, it's 22.04
Times 10
times negative 10.
times negative 10
Okay.
divided by negative 1.63 times 10 to the minus third. That's what this is.
Oh, maybe I calculated that wrong. I don't know.
Yeah. Remember, this is a negative 1.63, and then it's going to be times 10 to the minus third.
Oh yeah, that is the problem.
Okay?
Yep.
Okay. So that is roughly, and the book goes on to explain this, that is about 1,330 atmospheres of pressure. Okay, I said it would try to get through here at about 20 after. You guys got it?
Yeah.
I think we're mostly good.
Okay.
We should do like 100.
Okay, that amount of pressure, I mean, look at that, 1,300 atmospheres, it will lower the melting point by 10 degrees. But that got me to thinking, and we won't have to do this problem. Here it is. The solution is in the book. So you can take a peek at that. Here's one. Can pressure lower the freezing point of water on Minnesota's roads? By how much? So I'm kind of answering the question. So I just got to thinking, from that problem right there, I got to thinking, these 18-wheelers going down the road. Have you ever you've gone down the road when it's really, really cold? And I know they're putting salt on the roads around here, but there are times when you're going and you're going to say, this road is wet, but it's really cold. It's really cold here right now. Well, from the data and results from the one we just did, assume on each tire of an 18-wheeler exerts 3,000 pounds per square inch in pressure on the roadway. At what temperature would ice melt under this pressure? And so if you and we're not going to do it, but if you wanted to use that equals 1 atmosphere, and just think, so I'm thinking of an 18-wheeler, maybe weighs about 100,000 pounds. I don't know what they weigh. But the trailers are geared to 40,000 pounds, and then you got a tractor and a trailer and all of that sort of thing. So you could actually figure out, and I'll just leave that to you, if you want to do that and impress your friends with, hey, did you know that 18-wheelers can actually melt the road ice if it's above X degrees, above 28 or so? The actual 18-wheeler can melt the ice without any salt. And those are very rough. Is each tire give just a square inch of area? Probably not. It may be 10 square inches. So this is a very rough estimate, but it's an idea. This is just another application of this Clapeyron equation, looking at how much pressure does it take to convert coal into diamonds. And it's giving you the volume. Look at the big difference here. Here's coal or graphite. The volume and per liter, volume liters, and the diamond. I mean, that's a big change. The diamonds are a whole lot more dense than coal. 25% more dense. Look at, you almost got 1 unit difference out of 4, maybe about 20% difference. But you could just kind of go through this calculation. Again, you're calculating delta P. And it takes 65,000 bars. The author goes on to say that General Electric, like in 1957 or some year around then, actually got going with an industrial process to convert graphite into diamonds. And so they were industrially generating these kinds of pressures. Okay.
So do they make a lot of money off of it?
I don't know. It's good. It'd be good to look into.
The cost of energy to generate that long.
Yeah, but diamond tip drills and augers for drilling for oil and all that sort of thing. They put diamonds on those things, but I think they just use industrial grade diamonds. The dregs, the stuff that's not going to go on rings and earrings and all that sort of thing, but stuff that's clouded and this and that and the other things, but still pretty strong. So, but I don't know if there's economically viable route for that.
Well, like lab-made diamonds now, right?
Yeah, I think so. And
is that what they
probably
say?
That may be what that is. I don't know if they actually have a process for manufacturing diamonds. Okay, the Clausius-Clapeyron equation helps predict equilibrium pressures at differing temperatures. What's the equilibrium pressure going to be? And here's two forms of it. The differential of the natural log of the pressure is equal to delta H over R times dt over T squared And if you integrate this at P1 and T1, P2, T2, you get this form of the equation that you can actually use for some calculations. The natural log of the P1 over P2 equals the negative the delta H of the divided by R times this difference in the 1 over the temperatures. So that's the Clausius Clapeyron equation. All right, and let's just quickly, I promised you some time on chapter 5, so let's try to just take a minute on this. All liquids have characteristic vapor pressures that vary with temperature. The characteristic vapor pressure for pure water at 22 centigrade is this. And at 30 degrees centigrade, the vapor pressure is this. Use these data to calculate the change in enthalpy per mole for the vaporization process. So you're using this to actually calculate this. Change in enthalpy. Well, rather than us try to calculate it, let's look at the solution. All right, so the this is P1, this is T1, this is P2, T2. I don't know if you handle your word problems this way, but I would recommend it, is that you read the problem and actually identify what is in the problem. What are those numbers? And then, or even set up a little table of these numbers. But you can see they're not converting this to atmospheres. We've got this ratio. If we converted this to atmospheres, it'd be the same ratio. So you can actually leave it in millimeters of mercury and actually calculate a delta H of vaporization per mole of water based off of its vapor pressure at different temperatures. Okay, so keep that in mind. Some of your homework problems will deal with that. I don't know what else I had here. I can see grinding through some of these things would take us longer. Yeah, that's it. That's it. Okay. Let's go back here. Let's go to here. Let's go to chapter 5 homework. Okay, Liz, what's your biggest concern? Prioritize these.
4 and 7, all of us are stuck on, but it might be better to focus on the C's and D's of the problems we don't get and just throw out 4 and 7.
Well, let's look at 7. We'll look at 4 here, but 7. Well, let me give you a couple hints on 4, and we'll keep it. Okay, remember rice, okay?
Yep.
You did that. Mm-hmm. So initially you got 1.48, 0, and 0.
Yep.
And then they give us 0.4 of CO2 is made, so you can back calculate everything else.
And so what do you get?
0.2, and then
Wait, this
minus.
minus 0.2 minus what over here?
0.8.
All right, so what's the equilibrium concentrations?
0.2, 0.28, 0.4.
Okay, now I'm going to just give you a quick little road map. All right, quick little road map. Sum those, and that gets you the total moles.
Yeah.
Then divide the pressure of HCl, divided, or not the pressure, the moles of HCl divided by the total moles gives you what?
Mole fraction.
Mole fraction.
So the total pressure is just going to be 1 atm?
Right.
Okay.
So the partial pressure of the HCl is going to equal the mole fraction of HCl times 1.
So then that's going to get you your Q or your K. If you, when you figure out the partial pressures for all of those,
That'll give you your K.
they'll give you K. And then you plug that in and do...
Oh, I see. Ooh. Oh, okay. Okay, I can see where you might be. That's going to give you your KP at this 386 degrees centigrade, isn't it?
Wait, how is that giving us our KP?
Well, KP is going to be, or Q. The K at 386 degrees is going to be your partial pressure of HCl divided by 1 squared. No, wait a minute. I'm sorry. We need products in the numerator. So it's going to be the partial pressure of the chlorine squared. They're all divided by 1 times the partial pressure of the water squared divided by the partial pressure of HCl to the 4th power times the partial pressure of oxygen. To the 1st power. And you can stop right there. There might be some discussion about what is that a K, is that a Q, is that a KP naught? KP naught would suggest it's at 298 degrees. But
So that doesn't... So the answer for number 4 is wrong.
what answer does it
For
have?
4 it says KP equals 73.
And how, why do you think
Because I did that. Like,
Yeah, I don't think...
And I didn't get 73.
I don't think that gives you 73.
Yeah, it does.
Why did you do
You
that?
did it off of mole fractions? Or total?
No, I see what I did wrong.
Yeah, if you do it based on mole fractions, you should get 73.
Okay.
You might not get 73.1, you might get 73.3, but you'll get close. All right? Depends on how you round off your mole fractions, or whether you round them off. Okay, so you can do 4. You can do everything with 4 and 7, is that right?
No, there's lots of parts and problems that we're struggling with.
And
Yeah.
I think there's 2C.
Or
Yeah, 2C is tough.
2C.
I have 8A done, but not... And I have the equations for 8B, but they didn't work.
Oh.
Like, I have a way that should work, but it doesn't.
Yeah, that doesn't seem like a good door.
No. Yeah. It just... I might have just done the math wrong. I have to go back to it.
Let me see what is it asking? Calculate the reaction at a 0.750 when the total pressure is 0.932 times P naught. So 0.932 of standard pressure. C. Okay, it's not grabbing me what to do with to say to encourage you on C. how do you go from that extent of reaction to when the total pressure is?
So we need to calculate Kp, and then we can use delta G reaction or equals delta G naught reaction plus RT ln Q, or whatever Kp is at that extent value.
Well, wait a minute. Coming out of part B, you have the same extent of reaction, 0.750, same total pressure.
So we should be able to plug in those partial pressures and get the right answer.
I think so.
But I have not been able to do that.
So you get in the partial pressure of carbon monoxide, hydrogen, methanol. But I think
Yes.
It should be right.
So I don't know the extent. How does the
okay. Well, you can calculate a delta G. What is this? 2C.
It's like ln Kp equals delta G over negative RT.
Well, you can just do delta G from the equation, right? With the
Right. You can get a delta G right off of their delta G's of formation.
We should ignore the delta G that was given though, because that's the liquid, right?
Oh,
But they don't give one for gas.
And you told us
so we just need to calculate
do it in pretend
that's
it's
gonna be the
gas.
problem.
It's labeled as a liquid and then give us a liquid one, but like he said, it makes it way too hard, so we need to do it. That's going to change all our answers or not.
Yeah, that may be why the numbers aren't coming out. Have you used the delta G for the methanol in any other part of the calculation so far?
No.
No? Okay. Well, then let's do a delta G for the gas, methanol gas.
So that's, I don't think that value's in our book.
No, I'm giving it to you right now.
Okay.
It's not far off, but it is a little different. It's off by about 4 kilojoules, but that's could be our problem. And then if you crunch through here with this equation, the delta G of reaction is equal the delta G naught that you get plus RT times the log of, well, this big expression that you're going to have the PI over P naught to the new I. And so really what that is going to look like, it's going to be the log of this. You're going to have the products divided by the reactants, right? Yeah, products divided by reactants.
Log of the products minus the reactants, all that to the power of that.
It's going to be the ln of that whole thing.
Okay.
The natural log of that whole.
To calculate partial pressures in V, do you need to multiply your mole fractions by 0.932, or do we just assume that P naught is 1?
Yeah,
Is that
assume
what
P naught is 1.
Okay, so if P naught is 1, the total pressure is still 0.932, right?
Total pressure is what? Yeah.
So
Yep.
to get partial pressures, in this case, to plug into this Q equation, we need to use mole fraction times
0.932.
Okay.
Right.
Then our delta G naught that we calculate, is that just from the table of values and the Q value you gave us?
Yes.
Okay.
Yeah. So hydrogen is going to be 0. Carbon monoxide is going to be whatever it is out of the table. All right? Okay. And, all right, let's see if we can do any damage to number 7.
We talked about 5B also.
Yeah, 5B.
5B?
I found an equation, but I don't know how to use it because there's multiplication.
Okay, we can scratch 5D. Okay, we can drop 5D.
Oh, we're getting rid of it?
Yeah.
Oh. Are you using your answer where you still get that and we can figure it out later?
5D, A, B, C. What is it asking? Actually, derive an expression for the log, the natural log of Kp is a function of temperature. 5D.
We're getting rid of C as well.
Yeah, that's.
C was super easy though.
There we go. Yeah, was C super easy?
If you
No, he was difficult.
if you did B, you just had to integrate it with respect to T, basically.
I don't like integrating things.
Yeah, well, I'll give you what I got here for D, and then you'll see why we're dropping it. KP. Oh, the final expression for D is the natural log of Kp equals divided by T, I guess. Yeah, minus 0.859 natural log of T plus 5.78 times 10 to the minus 4th times T minus 5.25 times 10 to the minus 9th T squared minus 233. Yeah, C, I guess I would consider C optional also.
So it's
Yeah, let's see, the x pred is the natural log of
0.
infinity, or, no,
log of three,
is that a good number?
yeah.
Number 7. What temperature?
A to 8A and B.
Oh, okay. I thought number 7 was the last problem.
Yeah.
7's okay?
No, that was
No,
one
7 is very
none of us can
difficult.
get anywhere on it.
At what temperature does Kp equal 7.50 times 10 to the third? Well, for A, find this equation.
Is this 6 moving right stall? Is that like K times T2 or is that just K at T2?
K at T2. So the K,
So we're not actually multiplying by 2.
no, not multiplying. It's it's, so think of it as K sub T2. It's the K at temperature T2 divided by the K at temperature T1. Time equals the delta H over R times 1 over T1 minus 1 over T2.
This is the same.
Yeah, is this negative? Because it looks like the same equation before, but I suppose natural log to be flipped. It's like the one you showed earlier in class.
I think that's why we got T2 first here and T1 first here. I think it is flipped. Yeah. Actually got flipped. Okay. And then on part B, think of T1. I guess think of T1 as 298.15 degrees Kelvin, and T2, no, T2 is infinity.
Oh, we're going up.
Yeah, so,
That would have been really easy if it was
well, 1 over infinity
Is 0.
zero. Yeah, 0.
is 0.
Okay. So you just, yeah.
Okay, so 1 over T2 is 0.
Yeah.
And then see, what is your unknown in there? What is the highest value of Kp? So then, yeah, so then your unknown is this right here.
Got it. It's K2.
All right, that's 7. 8.
So 8A is like similar to the problem we did in class, where you use delta S of reaction, delta H reaction, to calculate delta G.
Yes. There's actually 2 legitimate ways to attack that. That's 1. Did everybody hear Dominic? So on number 8. So yeah, you're gonna try to get down to a point where you can solve this equation. So you're going to calculate a delta H, you're going to calculate the delta S, and it's occurring at 298.15 K, and so you can calculate a delta G that way. And then so this is part A. So you calculate delta H, you calculate delta S, and plug it all into here, and you get a delta G. Part B, they're now asking you, well, what about if this happens at 310 degrees? And just some equations I'd point you to is this one. Delta H at 310 is going to equal the delta H at 298, which you've calculated right up here, right? Plus
Would be dt CP.
CP dt. So kind of you'd have to get the CP, kind of the change in CP going from glucose to lactic acid, and the change in temperature.
Oh, we want this change in CP?
Yeah, so you're integrating this from 298.
Well, heat capacities are constant, so why would we be integrating?
Yeah.
If we're assuming stuff's constant.
Well, what isn't constant are the materials. The 2 materials are changing. They each have a different CP.
How do you integrate over
Well,
different discrete values? So it's not like we're integrating over a continuous function to things.
Couldn't you just calculate it separately?
yeah, I guess maybe you're pulling this out in front. CP times delta T.
Yeah, what's CP with DP and your question?
your heat capacity.
What about the CP of reaction? So maybe we want lactic acid times 2 minus glucose. And then that's the number we want there.
Glucose. Yeah. Well, let's see. 2 times the lactic acid minus 1 times the glucose.
That's what we want to use
Yep.
for CP. Okay.
Yep.
And then do you calculate the new delta H in the second way? Delta H 310 equals delta H 298 plus delta CP for the reaction times D2.
Well, you can substitute this delta H here.
Very good.
I think you might be able to get at this differently. But yeah, so did everybody follow? The CP would be 2 times the lactic acid minus 1 times the glucose, CPs. So you're kind of getting a change in heat capacity. And then for the delta S at 310, look at equation 3.18. And that looks like something like this. This is CP over T dt. So it's a little different than the delta H calculation.
Oh, yeah.
And then is our T in that case 310?
The T underneath.
Yeah.
You're integrating. So that's going to.
CP delta T.
So it's going to come down to the log of the final temperature over the initial.
Wait, what's that natural octane?
Well, from integrating this 1 over T dt, integrating
Yeah.
it's going to distill down to the natural log of T2 over T1. So yeah, so that's going to equal, so delta S at 310 is going to equal delta S at 298 plus, again your delta CP times the natural log of T2 over T1. So Ryan, the T2 would be the 310. Okay? Is that enough?
Isn't that just an equation from your book?
Oh, we went over again. Yeah, right here. 318. Okay. So we'll figure out when this is due on Wednesday. This is chapter 6 homework. And yeah, let me see here. There's a couple cross out real quickly. Let's see
Oh, that hurts to read.
Yeah.
Ow. We'll figure it out in the book.
Yeah. 3D, cross that off. 3D. Yeah, I think that, I thought there were more of them, but that's 3D. All right. And the problems that I copied out of the text, some of them have the answers that the text are not. They're not included here where I have any answers, but you might find some of those answers at the back of the text. All right? Okay. I'll see you Wednesday. Are there classes Thursday or is Wednesday the last day of class? Okay. I only teach Wednesday, Friday. So I didn't know what's happening on Tuesday. I just knew I didn't want to teach it on Friday.
Yeah.